right? Thank you. So yes. So wide-range classification. The idea here is the following. So wide-range classification is a binary classification problem, and what I want to do is that I have two classes of samples, the positive ones that are here, for example, denoted in blue, and the negative ones. And what I want to do is to find a linear classifier between them. And what it does is that it achieves a value of the precision, which is greater than or equal than a certain threshold. So in other words, if the classifier predicts an example to be positive, then I want to have high confidence that in fact the example was predicted correct. Now, to avoid trivial solutions where I start slicing the data in such a way that I find this one example that is positive and predicted positive, in fact, I want to also maximize the reach, which in previous literature was defined as the number of true positives that I am returning. So if I compare to with accuracy, the issue with accuracy is that in accuracy, I try to combine both the true positive and the true negative. So I combine the two classes, whereas here I am really focusing more on the positive classes. So for example, if I try to maximize accuracy, what's going to happen is that a reasonable classifier, so if, for example, on SVM, in this example, we'll find something that is in between the positives and the negatives. Now, it turns out that in these examples, I have the positives that are one cluster down here, and the negatives come in two clusters. One in which the major one, which is up here, and then there is a secondary cluster that is down here, and it's really close to the positive ones. And because I maybe have a penalty for violation of the classifier, then this turns out to be what the optimal SVM will give me. But this optimal SVM, however, might have low precision because the entire secondary negative cluster is entirely misclassified. So instead, what I want is to have a classifiers that, granted, may not reach all of the true positive points, but it slices away the secondary negative cluster, and it focuses only on the on an area in which you find the true positives. So in this problem was had many applications, mostly, for example, in the case of databases where they have unbalanced data sets, record matching and entity matching. Basically, this means that you have your examples here are pairs of records in a database, and you're trying to find the ones that are repeated. And in this case, the data set is widely unbalanced because the number of repeated records is hopefully much smaller than the unique records. And in this case, looking at the accuracy is misleading because the number of repeated records is dwarfed by the number of repeated records is dwarfed by the number of unique records. And so previous papers in database consider exactly this problem. More in machine learning / web search, folks have looked at this, for example, when you have a default action that is available, and then in that case, you may want to find only the true positives. So, for example, if you want to be very sure that you classify a piece of email as junk, you want to do that only if you have a higher precision. Anomaly detection is also something that falls within this category because you want to find outliers or anomalies with high confidence. And then if you take extensions of these models where you run this repeatedly, this is also relevant to the design of scientific experiments. Because in the next, say, lab experiment, you want to choose the one that gives you high confidence that you will learn something useful about the physical system that you're looking at. So related problems starting from the grandfather of classification problem, like the open hemisphere, then followed by the maximum hyperplane consistency problem, where folks has tried to maximize the accuracy. And then another problem, which is maybe the closest way to this one, is the two-group misclassification problem. So in the two-group misclassification problem is, well, you have two groups, so it's again binary classification. And what I'm trying to do here is to minimize the weighted inaccuracy of the solution. So this has been studied extensively since the 70s and also, well, then much more recently than that. And one of the pieces of work that is probably more related to the kind of things I am going to talk about is also look at approximate algorithms. And this was based on the observation that sometimes it's not so hard to find a solution that is good enough. So it's hard to find, it's easy to find a solution that is good enough, but then you can improve over it. And this doesn't need to be the exact optimum. In fact, maybe you don't want it to be the exact optimum because a solution that is more heuristic could be more easily generalizable. So formulating the wide-reach classification problem as a mixed integer linear program. So I am going to have decision variables that are telling me what the classifying hyperplane is. And then binary decision variables are going to tell me whether an example was classified positive. And so then a precision threshold, which is the main hyperparameter of this algorithm, that is telling me that the if I look at the predicted positive examples, those have to exceed this precision. So I'm trying to maximize the reach subject to the fact that the precision is greater than or equal than theta, and then I have constraints that are basically relating the binary decision variables with the classifying hyperplane. And in all of this, going back to the long tradition of the two-group mixed classification problem, there are these parameters epsilon that are meant to avoid accuracy problems in the numerical solution of this. So I have this mixed integer linear program. I should solve it. But before doing that, I would like to talk a little bit about what happens if you try to look at the relaxation of this problem. And the relaxation, you can look at this as a linear relaxation. You can have more complicated models in which you have quadratic things going on, and that would be effectively an SVM. But effectively here, there is a large integrality gap. And the reason for that is that you have these constraints that are enforcing the binary values of these decision variables related to the hyperplane. And if you violate the hyperplane just by a little bit, this variable should flip from 0 to 1, whereas in the linear relaxation, they flip from 0 to very small value, and that is not very meaningful. And so you can look at this and say, well, I have a large integrality gap in general. I like to here instead show a more concrete example in which the positive examples are all clustered at the corner of the unit square, and then I generate a bunch of positive and negative examples spread uniformly within the unit square. And here the optimal classifier with high precision would be something that cuts one of the positive clusters, whereas if you look at the relaxation, it's going to be basically a random hyperplane. Now, the main difficulty of this problem is the precision constraint, which may make the problem infeasible. But it turns out that I can analytically say what is the value of a Lagrangian multiplier associated with this constraint. So then I take this constraint and I put it into the objective function. At that point, you get a two-group misclassification problem, which has actually a really nice structure compared to the general one. And so there are all kinds of things that you can do for branch and bound and to make the solution faster. And validation, so this results both in training and validation. Here I'm showing results in cross-validation, synthetic benchmark, real benchmarks. And in many cases, this algorithm is the only one that gives a feasible solution. So that's where the work is at this point. And the future work is there is lots of things to do. And with that, I think I'm going to wrap up.
Thank you. Questions?
How does RAGE compare with other kind of metrics which you use on data like F1 or something like that?
I'm not sure. I'm not sure.
Else? Yes, Roland.
Wondering whether you want to use like something like AUC to see the trade-off.
So the things like AUC or F-score metrics, they in general they seem to be perfect to this because I'm really interested in focusing on one of the two classes as opposed to combining things together. So I'm not sure if you have something specific in mind, but in general, in this actually goes back to previous observations, such as, for example, in the database papers that I was citing before, that these F-scores and AUC just don't seem to apply to this because, say, for example, you have a very unbalanced data set, then your entire AUC is just gonna look skewed toward the big clusters. So.
One last question.
Yeah.
I was wondering if you can kind of use the approach to identify maybe outliers or noise in the data itself to determine what is like the highly constraining data point.
I do think so. Anomaly detection, I think, is going to be a very promising application. However, at this point, I don't really have data to back that claim.
Okay, thank you again.